Hello everyone, this is Asha from Sri Venkateswara College of Engineering. Today I'm here to present you a video assignment on turning machine and automated simulators. So today we are going to look into the research paper on turning machines and automata simulators abstract. This paper introduces a turning machine and push-down automata simulators as a virtual environment for learning computational models and automata theory. The two-fold contribution of this work is an overall use of modern technology to improve learning and cognitive experimental evaluations of its use in context. A preliminary evaluation shows the effectiveness of the simulators in the classroom. Introduction. So, computational science is an interdisciplinary field in which mathematical models combined with scientific computing methods are used to study systems of a real world problem in practical use. It's typically the application of computer simulations and other forms of computation to problems in various scientific disciplines. One of such mathematical models is automata theory. The concept of automata theory, such as Turing machines and pushdown automata have important use in designing and analyzing computational models of several hardware and software applications. Our simulators are designed to tackle the issues and meet the active learning preference for computer engineering learners. So, the related works are there are a number of finite state of automata simulators which have been developed. Example 1, 2, 3, 7, 9, 10 to enhance the learning of automata topics. Most of them suffer from one or more flaws that make them less effective motivating as a learning tool, particularly for less advanced students. For example, the tools PETC in lack visual clarity and dynamic capability. They are also dependent on advanced mathematical and Indo-syncretic user interactions. On the contrary, our simulators are designed with a clear workflow of learning activities and hence it is easy to use and easy to learn for new users. The finite automata. The finite state machines or automata FA represent a mathematical model for several software and hardware devices. Automata have several applications in both software and hardware. In software design, it can be used in a wide range of modeling, from a simple text editor to a more sophisticated compiler. In computer gaming, it can be used to model puzzles, tennis games, and many others. So, informally, a finite state machine is a machine with a finite number of states and a control unit that can change the current machine state to a new state in response to an external effect or input. A sequence of input is said to be accepted or recognized by the finite state machines if the machine's controllers, starting from the initial states, scans all the inputs and stops to at one of the final states. The pushdown automata. A pushdown automata PDA is a finite automation that can make use of a stack containing data. So pushdown automata differs from normal finite state machines in two ways. They can be used to the top of the stack to decide which transitions to take, and they can be manipulated the stack as part of performing a transition. A systematic representation of PDA is given in the figure. So the systematic descriptions of the PDA is the input symbol, the control unit, and the stack. Here is a push-down automata research papers example. So the control unit scans the input symbols from left to right, starting from the leftmost one. Each move of the control unit reads a symbol from the input while at the same time changing the contents of the stack through the usual stack operations such as push and pop. Each move of the control unit is determined by the current input symbol as well as the symbol currently on top of the stack. The result of the move is a new state of the control unit and a change in the top of the stack. So we have here the formally it is defined as a seven tuple. So we have Q is the state and the sigma, this transitions and transition function and initial state and final state. So Q is a finite set of states. Sigma is a finite set of which is called the input alphabet. Then we have this is a finite set of which is called a stack alphabet. Then rho we have Q into sigma which is into P Q into T and this is the transition function. Q naught is the start state and Z is the initial stack symbol and F is the final state. So this is automata. The PDA is formally defined by this. And next we have turning machines. Turning machines are the most powerful finite state machines. They can simulate exactly what a digital computer can do. Informally, a TM. Turning machines consist of a finite set of states and a controller that can read and or write symbols on an infinite length tape. Unlike DFA, NFA, and NFA and PDA, tuning machines controllers can move in both directions on the tape. But more interestingly, tuning machines can be used to compute functions exactly the same way that modern digital computers can do. In this case, the function arguments are represented as a sequence of ones separated by zeros and are returned on the machine state. So the Turing machine simulator. As stated before, traditional lecture-driven style for teaching, learning, tuning machines is time-consuming and difficult for average students to grasp its basic concepts. So, in order to facilitate the teaching learning of a basic Turing machines concepts for average engineering students, a Turing machine simulator component is integrated into the environment. Learners can easily build their own tuning machines and follow in a step-by-step manner how the turning machines works on any given input. All operations of the turning machines can be simulated by this simulator. The component interfaces showing the turning machine simulators is shown. While the turning machines operates on its inputs, the number of short commands also appears on the editor to give the learners more information about the theory of tuning machines. The tuning machine simulators also includes sound effects to make learning more fun and interesting to learners. So here you can see the tuning machine simulators. So this is an input and output tape, and this is the state which is initially at the zero, and one it is pointing to the one turning machines. Then here is the sequence that turning machine simulator interface in the IE interface 010. So this is a turning machine example to add two positive integers. So as we can see in the paper, the tuning machines, the simulator pushdown automata simulators. So here is a PDA simulator interface. So this is the start state, Q naught, read A, push A, and then state Q1. This is the initial state, and then we have second one is the stack. Then the third one is we have here to run to the compilation, run stop by stop, and then we can adjust the speeds and so the highlight color visited. And then we have fourth, we have automata, and the fifth we have the graph or the what is that images the start state Q naught, then to the Q1, then to the Q2, and then Q2 and the Q3 is the final state. Then we have at the sixth position, we have the file to create and save and delete the files. The seventh, we have a blank space. So in the figure, these are the simulations of the numbers of 1 to 7 are explained as follow. Then we have tuning machine simulators, as we have seen in the picture. They have talk, clear, stop, fast auto, and auto, step, change state, and load and update. Then we have finite automata simulators. So then we have finite automata simulator, a push-down automata, and the turning machine simulators discussed in the previous sections are complementary work for previous finite automata simulators. So here we have robust based automata simulators. So 0 is the initial state and 1 it is self state to 1 comma 0. So 0 to 1 1 is going and 0 to 7 1 is going and 0 to 2 the 0 value is going. So here the 3 is the final state and 4 is the final state. 3 has a self declaration of 1 comma 0. So the remaining part of the input string is 1 1 0 1 1 0. We have add state, move state, remove state, and then we have connect states, remove connect, and select start, select accept, start new. We have various options to select. The current input symbols is 0. So we can set the language. We have automata simulators here, and we have NFA to DFA converter, DFA to RE converter, RE to lambda NFA converter, lambda NFA to the line NFA converter. So we can minimize, we can state size, and we have robo simulators, and we have various operations in the main simulator interface. So next we have the evaluation results of our robot simulated tools. So the design is 4.4 average evaluation point, user friendly is 4.1, functionality is 3.9, and automata simulator usability is 3.8. How it can help your automata learning process is 4. Now we can look into the conclusion. So in this work, we introduced the pushdown automata and turning machine simulators. And this purpose was introduce active learning simulators for novice learners for automata, the theory and related topics. As an evaluation step, the simulators were tested by students in the automata classroom. Then students experienced the interest and they judged the simulators on convenient learning tools in automata theory. So this we can conclude. Then we took the references of the papers like minimization and visualization of a finite state machines. Then we took visual automata simulators as a tool of simulating automata and turning machines. Then we have deterministic finite automata simulators, and then we took the research paper on towards a constructive approach to e-learning in software engineering and e-learning control in the corporate government. So these are the references used in this paper, and thank you